Good morning all. This is Satish Kumar, Assistant Professor of EC Department. Now let us see the another video lecture series on linear time invariant system in terms of continuous time. Linear time invariant system are characterized with the help of differential equation, impulse response, block diagram, state variable description and transfer function. Differential equation, it is used to represent continuous time linear time invariant system. It relates the input and output of the system. When we giving the x of t to the differential equation, which can produce the output as y of t. Differential equation has two components, natural response and forced response. This is the differential equation when we applying the input to your system function, which can produce as the output is nothing but your response as y of t. This is the impulse response of the system with respect to differential equation with respect to tau c, that is cutoff frequency, that is nothing but h of t. While we taking the impulse response of the unit step function, we can get the response of the system as it related. It is the linearly growing function with respect to 1 minus e power minus of t is nothing but the impulse response of the differential equation. System transfer function can be defined as ratio of the output to the input. H of s is equal to y of s divided by x of s. Frequency response, h of omega is equal to y of omega divided by x of omega. When we applying the time domain function to your Fourier transform, which can produce the output as x of omega. Then applying again frequency domain analysis, we can produce the output as y of omega. While we applying the inverse Fourier transform of y of omega, we can get it as our output as y of t. Next one, condition for an LTI system to be causal, h of t is equal to 0 for t less than 0. Condition of an LTI system to be stable, summation k is equal to minus infinite to plus infinite. Modulus of h of k should be less than infinite. Impulse response is the output generated by the system when the unit impulse is applied to the input. When the del of t is applied to your input of an LTI system, which can produce the output as h of t. Therefore, h of s is equal to y of s divided by x of s. Therefore, h of t is equal to, while we taking the Laplace inverse of h of s, we can get the h of t as impulse function. Unit impulse function can be defined as del of t is equal to 1 for t is equal to 0, 0 for t should be not equal to 0. Next, this is the time domain into frequency domain. While we applying the inverse, while we taking the Laplace transform of x of t, we can get x of s. While we taking the Laplace transform of h of t, we can get h of s. Therefore, h of y of t is equal to h of t into x of t. While we applying the inverse Laplace transform, we can get y of s is equal to h of s into x of s. While we applying the above inverse Laplace transform function, we can get y of t is equal to h of t into x of t. This is the time domain to frequency domain representation. The whole wave can be represented by d, that can be converted into frequency domain in terms of 1 kHz. The whole wave can be divided into half as t by 2 t by 2. In terms of frequency domain representation, it can be represented as 2 kHz. How to find the impulse response? First, we can find the differential equation. For the differential equation, we are applying the Laplace transform. For that Laplace transform, we can find out the algebraic equation and then solving for roots. Finally, we can take the inverse Laplace transform. We can get the impulse response of the system. Any input can be represented by unit impulse function, that is nothing but x of t is equal to, while we applying the LTI system, which can produce the output as y of t. Convolution integral, while we applying the convolution, y of t is equal to h of t into x of t, h of t into u of t. While we applying the convolution integral of integral over minus infinite to plus infinite h of tau into u of t minus tau, we can get the function as 1 divided by a into 1 minus e power minus at into u of t. While we applying the unit impulse function to e power minus at, which can produce the output as y of t. Convolution integral can also be defined as y of t is equal to h of t into x of t or x of t into h of t. Y of t is equal to integral over minus infinite to plus infinite h of tau into x of t minus tau into d tau. Next, this is the another convolution representation for all the conditions when a is equal to 0, a greater than 0 and a less than 0. For t, a, t or a, whatever may be, we can get the representation as it is. We can get the representation as y of t is equal to 1 by a into 1 minus e power minus at into e of t. With the help of convolution integral, we can applying the condition, we can get the results as 1 by a into 1 minus e power minus at into e of t. Next one, this is the another representation of convolution integral. First we can find out there my x of t and then find the h of t can be given. We can find y of t is equal to x of t into h of t. Now we can substitute h of tau is equal to 0 to 3 and then t minus 4 to t plus 1 we can get the increasing t with the, we can considering the overlap cases as t increases. This is the convolution integral setup. Next one, properties of convolution integral. It can be of three properties: commutative property, distributive property and associative property. Commutative property can be defined as x of t multiplied with h of t is equal to h of t into x of t. Distributive property, x of t multiplied with h1 of t plus h2 of t, which is equal to x of t multiplied with h1 of t plus x of t multiplied with h2 of t. Left hand sided block diagram representation: x of t multiplied with h1 of t plus h2 of t, which can produce the output as y of t. Then x of t multiplied with h1 of t, again multiplied with h2 of t. Finally, we can going to add, we can get the output as y of t. Associative property, x of t multiplied with h1 of t, again multiplied with h2 of t, which can produce as x of t into h1 of t into h2 of t. Similarly, there may be interchange. X of t multiplied with h1 of t, again multiplied with h2 of t, which can produce the output as y of t. X of t multiplied with h1 of t into h2 of t, which will produce the output as y of t. Now we can see the assessment. Define LTI system, linear time invariant system, to identify the continuous time systems with the help of differential equation, impulse response, block diagram representation, system variable representation. The system transfer function is given by ratio of the output to the input. H of s is equal to y of s by x of s. List the properties of convolution integral: commutative property, associative property and distributive property. Dash relates the input and output of the system differential equation. What is mean by impulse response? When the unit impulse, that is nothing but del of t, can be applied to your linear time invariant system, which can produce the output as impulse response as h of t. The condition of an LTI system to be causal is given by h of t is equal to 0 for t less than 0. Associative property is defined as x of t multiplied with h1 of t, again multiplied with h2 of t, which can produce the, which is equal to x of t multiplied with h1 of t into h2 of t. The condition for an stability of an LTI system is summation k is equal to minus infinite to plus infinite. H of k should be less than infinite. Thank you.